Okay, everybody, welcome to the Internet of Things podcast RF sensing event. I have an audience from around the globe, but I also have a set of panelists from around the globe here to talk to us about RF sensing. So I am actually going to have each of them introduce themselves and tell you a little bit about one of the four technologies we're going to be covering. But first, I just want to tell you why I'm super excited about this. I deal a lot in the smart home. And when I think about what's wrong with the smart home, a lot of things are missing, primarily context. We aren't able to give our sensors and computers enough information about who's in the house, where they are in the house, where they are in relation to things, and where they are in relation to people. And a lot of people might think the solution to this is cameras everywhere, which feels really intrusive and really bandwidth intense and privacy worrisome. So RF sensing offers a way to get a lot of information about things and context without, one, absorbing so much bandwidth. A lot of the processing will happen locally on the device, and it gives more resolution with less computing power. So I'm really excited about this because I think just like my Roomba now knows like where a stairwell is and not to bump into things, I think a lot of our things will soon be able to tell us way more information about the world around them and the people in that world. And we're going to talk about a lot of different ways to do this because there are many and they all have their drawbacks and I guess their pros and cons. We'll call it that. So welcome to this event. And now I'm going to have my panelists introduce you to themselves and the particular technology I assigned them. We'll get started with, let's see the poll. I'm going to see which one y'all are most excited about. Let's see. Quick vote in the poll. Tell me which one y'all want to hear about first. Oh, Wi-Fi 802.11 is winning by a lot. So I'm going to have everyone start, or I'm going to have Chris, please start and tell us who you are and a little bit about Wi-Fi 802.11bf.
Sure. Thanks, Stacey. I guess I just want to start by saying thanks for inviting me to participate today. I can say we certainly have an excellent panel and a very interesting agenda to go through, so thanks for that. I also want to say I remember the first time that we met and we were chatting, of course, about sensing. And as we got into it, I started talking about waveforms. And I remember you were pretty excited by this and definitely wanted more. So yeah, thanks again for inviting me. And I'm happy to, hopefully get into some more details about this as we go further. So that being said, hi, everybody. My name is Chris Bagg, and I work for Cognitive Systems as a senior wireless systems architect. My background's actually in semiconductor. I've worked for quite a while as an analog mixed signal IC designer. In the past, I've worked on various low power DSP products, and I've also delivered designs for communication applications. But these days, since Cognitive isn't making chips anymore, my focus is still very low level, but I work to help bring Wi-Fi sensing into some of the major consumer Wi-Fi chipsets. In addition to this, I also chair the Wi-Fi Sensing Project Group within the Wireless Broadband Alliance. And this is a group that's been together and working together and talking for about the last 3 years. And we've produced 2 major publications, and we actually have a third one that's on its way. So for those of you who are interested, I highly recommend going to the WBA's website and downloading some of those papers, and you can learn quite a bit more about the technology from there. So yeah, I'm going to talk about Wi-Fi sensing, of course. But before I introduce it, I want to start by talking about maybe a broader topic called Joint Communication and Sensing, or JCNS for those of you who like acronyms. JCNS is becoming a pretty hot topic, especially in the academic community these days, because the goal is to use the same physical hardware and signals for both communication and radar sensing. This is a very interesting concept, but designing a transceiver for communication and sensing is quite a bit difficult, and they have different requirements.
Oh,
so
wait a second, Chris. Chris, we'll get into some of that, but first, I really want you to focus on getting us excited about 802.11bf.
Yeah, sure.
Just telling us what it is. Sorry, because I was like, oh man, you are giving us this before we get excited. We got to get excited first.
Yeah. So yeah, Wi-Fi sensing. What I was going to say is, yeah, why do we want to use Wi-Fi for this? You know, Wi-Fi is everywhere. Wi-Fi is got a major infrastructure. You know, it's a low-cost device that everybody's adding into their products, and it's very well suited for sensing. You know, it's one of the primary technologies that we use for connectivity, and you know, it's driving really the adoption of the smart home. So what it enables us to do is basically add radar functionality to some of the existing devices almost for free. A lot of this is possible with Wi-Fi the way it is today, but there are some disadvantages. There's some gaps that are you know, in the standard that require some proprietary components to be used. But what 802.11 BF is doing is they're looking to address some of those gaps and create more standardization and more you know, compatibility to eliminate all of those proprietary pieces. And what that's going to do is that's really going to help further the adoption of this technology. And you know, it's also going to open up the ability to you know, create more use cases that maybe we haven't even thought of yet. So yeah, certainly a very exciting topic. So I hope that kind of gets everybody going on the 802.11 BF area. So maybe I'll pause here.
I'll add a little bit because you know, this is so far out. 802.11 BF is something that won't be standardized until like 2024, correct?
That is correct. Yeah.
So until then, we're kind of, oh, go on.
No, I was going to say you're exactly right. The group's been working for, I'd say, maybe 2 years. The process in IEEE is quite long and it's quite extensive, but the end result is, you know, a very well thought out published standard. And we can see this over the last 20 years, Wi-Fi has been around. We have backwards compatibility. We have, you know, a phenomenal standard, but it does take time to develop. So just to add to what you said, yes, 2024 is the deadline for when everything's going to be wrapped up, but there are some intermediate steps. The next one is actually January of next year, and that's going to be the very first draft 0.1. So that's definitely an exciting milestone.
Okay, first draft coming January of 2022. I'm excited about this because it's going to give us the ability to track people moving throughout spaces. It's maybe not as fine a resolution, but you know, right now we're looking at things like motion detection. There's the possibility of one day doing fall detection. So we'll talk about some of those use cases in a bit. Now we're going to go, let's see, back to the polls to see. I know this is unfair because we're still moving in the polls, but I've got UWB as my next most popular technology. So let's get Ramona to talk just a little bit, introduce us to the technology, the use cases that are happening, where it could go.
Hi,
Ramona,
thank
you're
you,
on mute.
Stacey. I mean, yeah, thank you for the invitation. I'm Ramona Malfievich. I'm a lead IoT engineer at Digital Catapult in London. My background is in computer science. I have a PhD in wireless sensor networks, and in the last 10 years, I built design solutions based on range or long range, and a couple of strange and harsh environments and other harsh conditions. I also work, I'm a member of the IoT group of the British Standards Institute, and today I'm the ultra-wideband champion in this panel. So ultra-wideband is a technology that actually has returned to the forefront of research and market interest after a decade, I think, of oblivion. And this is thanks to a small, cheap, new ultra-wideband impulse radio chip that was designed by the Irish company Decawave. So this is how ultra-wideband came back into our life, because it was present in 1920, then it was forbidden, used only by the army, and then it was resurrected after many, many years when we started to be allowed to operate in certain frequencies. And it happens because it was actually using a lot of the spectrum. So that's why it was banned at the beginning. What is ultra-wideband? Just a tagline. It's a technology that is based on impulse radio, so it's using very narrow pulses in time and spreading the signal energy across a very large bandwidth. What does this mean? As I said, large bandwidth, reducing the power spectral density. It reduces the interference to another technologies, which is an advantage of ultra-wideband. And actually, it reduces the impact of multipath components. So ultra-wideband as well enhances the capability of ultra-wideband signals to propagate through obstacles. It propagates through walls, and it actually simplifies the transceiver design. And the large bandwidth also that comes with the technology provides excellent time resolution, which we like a lot about ultra-wideband, because it is enabling the receiver to precisely estimate the time of arrival of a signal and distinguish the direct path from multipath components, problems that we have with other technologies, especially by measuring and analyzing some channel impulses responses. So it's a fantastic technology for estimating distances, for ranging, and for localization for the moment.
What doesn't it do? What's it bad at?
What is bad at? I don't know what is bad at. I'm not going to say it, but it consumes a lot of energy. So we still have to work on that. And we cannot use it outside because it's forbidden. We cannot deploy the infrastructure based on ultra-wideband outside.
Oh, well, I have questions about that. So we'll ask those in a minute. All right, radar looks to be next. So Marcus, why don't you introduce yourself and radar? And you're on mute. Just so you know, so unmute.
Hi, everyone. My name is Marcus da Silva. I'm a distinguished engineer for NI, also known as National Instruments. And NI is in the business of building test and measurement equipment. And I have spent most of my career building test and measurement equipment at various different companies, concentrating on RF microwaves and things that travel through the air. So my background is, okay, some of these other folks who will build equipment, I've got to figure out how to test and measure it and make it work. Okay, so radar. Radar has been around for quite a while. I think the first radar was actually built around 1904. It has been very much in use in the military since about World War II. Okay, the basic idea of radar is that you take a signal, an RF signal, you send it through the air in a particular direction. It encounters objects in the way. Those objects will reflect the signal. You receive the signal back again. And by measuring what's been reflected and comparing it to what you sent, you can learn many things about the object. So for example, the time of flight is related to the round trip path delay at the speed of light. Okay. The frequency shift or Doppler shift tells you the relative velocity of the transmitted and the receiver. You can measure velocity. The amplitude of the received signal tells you something about how big the reflector was. So if you've got a 747, it's going to reflect more than a Cessna if it's in an airplane thing. Okay. A couple of other things that we talk about in radar. You have something called a monostatic radar. That's where you have the same antenna receives and transmits. Okay. A lot of times we use bistatic radars, which means you have a different location for the transmitter and receiver. Okay. And in some of the radars used in handheld devices, we use sort of a combination of things. They're bistatic, but the antennas are very close together. You can do some interesting processing with that. All right. You also got passive radar. In an active radar, you send signals out and you look for the return. In a passive radar, you use signals that are present in the environment, kind of like your eyeball. Your eyes don't shine lights. They simply use sunlight or ambient light. Okay. And let's see. Radar also has several different processing methods. The original ones were pulsed. Okay. We got Doppler radar. It's used in weather. We have coded radar where you assign a digital code to the signals and it helps you bring the signals out of the noise and make them more sensitive and things. You also have stealth radar. Okay. In stealth radar, you don't want the enemy to see where you're transmitting. You try to make the radar mimic something in the environment or hides inside of the signals in the environment. Okay, so that's radar in a nutshell.
So I was like, which should we focus on for things like the smart home applications, or maybe the wellness applications like Soli or?
Well, we should probably focus on short range radars that can distinguish, have fine angle resolution, fine distance resolution, but they don't have to see a 747 at 10 miles away.
Yeah, if that's coming to my house, I'm in a lot of trouble.
Okay. All right.
No smarts will help me there. Okay, so we'll talk about that. All right, and Bill, don't feel bad that LiDAR is not like everybody's favorite yet. Maybe this is your chance. You can be
But
like,
I voted
Bill.
for it.
Marcus voted for it. All right, so tell us a little bit about LiDAR, which most of us are familiar with because, hey, it's on cars, and what is happening to bring it into consumer devices and the iPhone, actually.
Yeah, so I'm Bill Flaherty. I'm the hardware engineering practice lead at Berry, which is an IoT engineering firm. And so, yeah, I'm going to talk a little bit about LiDAR. So LiDAR actually it has various definitions, I think, but light detection and ranging is one that you'll see a lot, right? And so the basic idea is that you use a laser to illuminate a target, and then you measure the time of flight of those that light back and forth as it scatters off of the thing that you've illuminated. Typically, we talk about lasers in the IR a lot if it's propagating in the air. You'll see stuff in green light if you're doing like bathymetric LiDAR, where you're trying to measure like depth of body of water or something like that. But really the benefits of LiDAR, right, are that you can get incredibly high detail. If you've ever seen topographic maps that are LiDAR generated, they're absolutely incredible. It's been used a lot in archaeology to find sites that are hidden or hard to get to, and it's really impressive. And then, like you mentioned, Stacey, right, self-driving cars are probably the big hot application. The one that I love is the Ingenuity helicopter that's currently on Mars, uses LiDAR to detect altitude and know how far it is off the ground, which is really cool that there's a LiDAR on Mars right now.
And
but
Zigbee.
Really,
sorry, I have to get excited. And Zigbee to talk back to its. Okay.
But I think, like you mentioned, it's starting to get more in reach for consumer devices. And I think that's kind of a combined development driven by the ability to build lower power lasers, like chip level diode lasers, things like that, as well as the ability to electronically steer the beam, right? So like to get really detailed LiDAR data, you need to be able to move that beam and scan it around. Something like your iPhone focusing mechanism, that's like the literal basis level of LiDAR because it's just a single direction, right? It's just measuring range. If you want to get any sort of topographical information, you need to scan that laser around. And the ability to do electronic beam steering, I think, will really allow for these smaller compact applications to get highly detailed data that before you needed kind of this big spinning thing on the top of your car in order to collect. So I think those developments are going to see us drive a lot more LiDAR into consumer applications.
So LiDAR is still relatively expensive. Where are the applications that it's going to be worth the bill of materials cost, basically, of sticking? I mean, is this something I should see on my, I don't know, my Roomba? I'm just going to use my Roomba a lot in this talk, but.
Yeah, I think anywhere where you need really detailed 3D information about the space that you're in is where you'll see LiDAR really. And, the bill of materials cost is high now, but I think what interests me is that it's going to start dropping significantly over time, right? And so we might not see this in, the 1 to 2 year time frame, but the 5 to 8 year time frame, as these components start to get a lot cheaper, then it could get a lot more attractive. I think the other thing that it'll combine with as well is like machine learning edge compute, right? Because a lot of LiDAR processes are incredibly processor intensive. So being able to do more on the edge and then maybe leverage things like 5G to get data back and forth at higher throughputs will really enable that kind of application.
Got it. I'm waiting for like my smart, how there's the smart fitness systems like the Tonal and Tempo. I'm like, you get some LiDAR in there and then poof, you can see like how poorly my yoga stances are. Okay, Ramona, I had a follow-up question for you on ultra wideband, because you said we're forbidden from using it outside, but I know that like, if I'm thinking about like Apple's Find My network in the tags, those are running around all over the place. So can you give us a little clarity on that?
Yeah. So I was not referring to the tags. So I was referring to using ultra wideband with a fixed infrastructure. So that's not yet allowed outdoors, neither in US nor in Europe, and it's forbidden by regulations. Yeah.
Okay, so if I'm thinking about mobile, because I feel like a lot of I feel like the use for ultra wideband is connecting people, like something on a person that helps tell other devices where they are with fine proximity.
That's a device-to-device communication. I'm talking about the type of device to an anchor communication.
Right. Okay, so in the device-to-device communication, that's something that's out there now. What are the use cases that you can see making that maybe, or that could be compelling there? Beyond just Find My.
Thinking about this time, social distancing.
And are people using it for that? Oh.
Yes. So last year, we were benchmarking a couple of social distancing solutions that are not based on infrastructure, so peer-to-peer, that were used by several companies because they wanted their people to return back to work in several industries, but they also wanted to ensure that the social distancing is enforced. So people were wearing tags. Some of them were having a combination of Bluetooth and ultra-wideband technology. So Bluetooth used to discover the neighbors in range, and then ultra-wideband to quickly compute the distance and then raise an alarm if there was a violation. Or I've seen social distancing solution based only on ultra-wideband. So the ultra-wideband radio used for both neighborhood discovery and ranging. Of course, paying the price of the high energy consumption of ultra-wideband, which is high compared with Bluetooth at the moment. Still high.
Which is why it's usually used in conjunction?
Yes.
Okay. And Marcus,
Yes.
Let's go into some of the details. You don't actually, and now y'all have introduced your technologies. Feel free to like show me your hand if you've got something to say about another technology. Y'all do not have to stick with your tech forever. And I'm coming back to you in Wi-Fi, Chris, don't worry. Marcus, let's talk. So on radar, which I also think of as giving a little bit of depth and giving a little bit of velocity kind of time information that UWB can give me, where does that fit in when compared to ultra wideband? What is the advantage of radar over something like that?
So radar can be ultra wideband. Okay. In fact, many of the radars are. For example, the Soli radar uses a 7 gigahertz chirp, which is fits the definition of ultra wideband. Okay. So the sort of the angular resolution is related to the wavelength of the radar. Okay, so smaller wavelength, higher frequency means you can resolve angles better. The distance resolution is more related to the bandwidth of the radar. So ultra wideband means that I can resolve distances better. Okay.
Okay, so
go ahead.
Using ultra wideband radar, I can see things farther away.
You can see things. You can see more resolution. You can see things. You can resolve distances better. Okay.
I can see how far away things are.
How far away things are, and you can say something, 10 centimeters away or a meter away from something 1.2 meters away. Okay. Whereas a narrow radar, you could not tell those two apart. They just look like one blob.
Got it. Okay. Now, so Soli is using ultra wideband because it's really important to know, like it's measuring my breathing. So Correct. It's measuring something Correct. Pretty, okay. This is good. Yeah, this is where I feel like people are like, I don't know why I would use what radio.
So Soli, for example, uses a 7 gigahertz chirp, which gives us something in the order of a couple of centimeters of potential resolution. So you can tell objects that are just a few centimeters apart.
Got it. Now, it doesn't work from super far away, though.
No, it's a low power device. It works a few meters at most.
Got it. Yes, which is why Which is why I can tell when I'm sleeping, but not when my husband is sleeping across the bed.
Yeah.
So there we go. I hope. There's no guarantees. All right. So let's go back to, I guess, Wi-Fi, simply because there's versions of this. It's not the official version of Wi-Fi, but there's version of Wi-Fi sensing today. And what is it good at, Chris? It's and what is it maybe not so good at just yet? And you are on mute. I'll just let you know before. There you go.
There we go. Yeah, so I think Marcus mentioned very well that you have the two trade-offs of the wavelength and also the bandwidth. Wi-Fi is kind of I would say maybe stuck a little bit in the middle. Bandwidth is king, but Wi-Fi does operate in it's a band that has fixed channel sizes, fixed bandwidths, and there's a lot of contention because a lot of people use Wi-Fi for pretty much everything. So we're limited to 20, 40, 80, 160, and maybe soon 320 meg channel bandwidths. And that limits, for the sub 7 gigahertz band, what sort of resolution you have in your sensing application. On the other side, Wi-Fi also works in sub 7 frequencies and also 60 gigahertz. And there's some trade-offs there as well. The lower frequencies, 2.4 and 5, they typically propagate through materials much easier than 60 gigahertz would, for example. So because of that, you could use the lower sub 7 frequencies for larger distance detections because they propagate through the materials much easier, and you can receive the reflections before they're attenuated well below the noise. 60 gigahertz, on the other hand, is interesting because there are very wide channel bandwidths. It's 1 or 2 gig. I can't remember exactly how wide it is. But it gives us a lower detection region because the power is limited, the propagation effects and attenuation is quite high. So it's more difficult to do long range sensing with the millimeter 60 gigahertz band frequencies. So, I mean, it's kind of stuck in the middle. There's pros and cons, but there's a lot of options as well. So it's quite interesting.
So the pros are it goes through walls, but at that, at the lower levels, like 2.4 and 5 gigahertz where we're doing it, it's not as fine grained. So it'll see big movements like, hello, Mayday, but it will not see help. Or maybe it would see that, I don't know.
Yeah, exactly. That's exactly it. It's really a trade-off, and it depends on the application you want to use it for. Sub 7 is fantastic. It's everywhere. It's in everybody's house. It's great for longer distances, so greater range, but maybe not so great compared to the 60 gig for resolution. So,
and it can't tell things like velocity, right? So it's not going to be. It's going to tell it. Can it determine like how quickly I'm moving? And I don't know about its time. It can. Okay, so Marcus is like,
yeah, yes. You can. All the information is there. It's exactly the same as radar. It's just the data is presented in a slightly different way.
Right. That's what's so confusing for most normal people about this, who are like evaluating these things. So if I'm evaluating using Wi-Fi, some of the questions I might want to know, like how much power do I have? Yes. And what's I think really exciting is once this is standardized, you'll be able to use other devices in the home that use Wi-Fi. So I might just bring in the computer that analyzes the signals basically. And then my other devices would also suddenly become part of the sensing network. Is that how I should think of this in the future?
Yeah, there's a little bit more processing that has to occur. I mean, even with radar, there's processing that has to occur. With Wi-Fi sensing, it's no different. You don't, the output of the sensing system isn't velocity and distance. You have to do a little bit of computation to get those values. But yeah, that's the goal with 802.11bf. That's to open it up and make it widely available for different devices, access points, client devices, whoever, to utilize these waveforms and these signals to extract this sort of information.
There's also the possibility of using passive radar techniques, right? Where you use existing, since Wi-Fi is everywhere, you use existing signals to figure out where things are.
Exactly. Yeah. Yeah. Exactly. Which is really cool because the signals are there already. You don't have to transmit anything. Somebody else has transmitted for you.
Mm-hmm.
So what are the implications of that for people who are like, wait, what? Marcus?
There's kind of two approaches. So you have the multi-static and the bistatic. So the multi-static is you have multiple devices throughout the environment, and as it transmits, the receiver can measure the transmission from that device and compute these quantities, these physical quantities from those transmissions. You have the bistatic, which the same device as the transmitter and receiver. I guess this is more similar to traditional radar, like a police radar gun would transmit and receive the signal at the same time. But then you also have the multi-static case where you're relying on the existing device communication and transmissions to obtain this information. So you're basically just sitting there listening to all the other traffic that's going over the air, all the signals that are going over the air, and you're extracting information from those signals. So you're not required to transmit anything additional. It's transmissions that already exist.
Okay. I was thinking about what are the implications for products and eventual use cases, like the pros and cons of something like that. I don't know if Bill or Ramona wants to hit that.
I think one of the big pros is just not having to put additional hardware into your device, right? Like anytime we're building something, we're looking to, minimize the bill of materials, minimize the size, the power use. And if we can, use the Wi-Fi equipment that's already in the device for communication to double up as a sensor as well, you've basically doubled your value out of that board real estate without having to add anything additional, which is really exciting.
Yes. Okay. Let's talk about 60 gigahertz because we're talking about bringing 60 gigahertz for Wi-Fi. Ultrawideband, or actually solely runs in the 60 gigahertz space, making it radar, UWB, and 60 gigahertz, which confuses the heck out of a lot of people. So let's talk in just very broadly for people. 60 gigahertz is good spectrum. Like Chris mentioned, it's huge channel widths, which means you can send a lot of data, but you can only send it short distances because it doesn't do well through walls. So that's the important thing to note. But let's talk about why you might want to operate in those channels for your various technologies, I guess. Go ahead. Raise your hand or just start talking.
I can kick in something here.
Go, Marcus.
All right. So 60 gigahertz is an interesting band. Okay, it's a half a centimeter roughly wavelength, and it has some properties in the atmosphere that make it that are kind of paradoxical. 60 gigahertz is absorbed really strongly by oxygen atoms, which means it doesn't go very far. Okay. However, that's an advantage because it means that it doesn't go astray. If I aim a beam of 60 gigahertz and I'm off beam, I'm not going to receive very much. So it's secure. Okay. It also means that I'm not going to cause interference with someone far away. Okay. So people can reuse 60 gigahertz in lots of places. And that coupled with the ability to have wide bandwidth signals, ultra wideband or high data rates, etc., makes 60 gigahertz a really, really handy band to do things like radar, and also to have really wideband communications, high data rate communications.
Got it. Any other comments, thoughts on 60 gigahertz? Are we like, okay, y'all are like, we're done with that. Okay.
Maybe one other thing I can say. So just to compliment Marcus, I actually think 60 gigahertz is probably a better technology for sensing than communication, which is kind of funny. But you can also do some very interesting things at the RF level. You can create what they call an antenna array, which is basically multiple antennas, 16 or 32 seem to be typical array sizes for 60 gig. And what this lets you do is this lets you direct the energy that you transmit to a specific direction. So now instead of the device being, transmitting kind of like a laser pointer, you can steer that beam to different locations in different directions, which is extremely cool. And for sensing, that's exactly what you want to do. You want to scan the environment. So, that's one thing that you can't do with the lower frequencies because the antenna array would be too big. It'd be like the size of a table.
And with 60 gigahertz, it would be the size of?
It would fit in your phone. It would be a couple centimeters square.
Yeah.
Bill, I just have to ask because, go on.
Go ahead. No, yeah, like the Soli radar, right? It's, the antenna array is just a few centimeters. And it has it synthesizes a 16 by 16, I believe.
Oh, wow. Okay.
Okay.
That's a lot. Yes. Okay. And now when we talk about sensing at 60 gigahertz, it sounds a lot like LiDAR. So it sounds like the same sort. Can you get the same sort of depth in information, Bill?
from 60 gigahertz as you can from LiDAR? Is that the question?
Yeah. Or any.
So I don't know that you'd get the same level of resolution, right? Because LiDAR can give you very, very, precise and accurate measurements. And then the other thing with LiDAR is you'll get a lot more range, right? So like an IR beam has that penetration through the atmosphere. And so you can, maintain that kind of coherent beam for, kilometers even, depending on the wavelength that you choose. And so that's why, you can have a plane that does, LiDAR scanning of topographical things like that. So, but, LiDAR is going to be likely more power intensive, more computationally intensive, and more expensive. And so they have their use cases, right? They're complementary technologies, but I don't think you can use one in place of the other, really.
Okay.
I like to think of LiDAR as something that gives you high resolution images, and radar is something that gives you, if it's an imaging radar, maybe resolutions in this few centimeters versus LiDAR microns.
Okay, so it's kind of like maybe how I see in the dark. I walk into a room, I can not see in the dark, but like a low lit room, I can't see any of the details. But I can see like this is a table I should not look into. Okay. Let's talk about privacy, because someone brought it up and it was my next question after 60 gigahertz anyway. This isn't a camera in people's homes. So a lot of people are going to be like, yay, fewer cameras. But it is the ability to tell like how I'm breathing, as in the case of Soli, or, exactly where I am in space does create some privacy issues. You're sending the data to a computer, but that can be trained to find all kinds of stuff. I always say, you could use radar to see when I'm sitting at home picking my nose if you wanted to. And I don't think people really want that in their lives. So how do we think about this with regards to privacy? I know y'all are engineers, but I also feel like it's your job as engineers to think about this sort of thing. So I'll open that up, and whoever wants to talk, go for it.
Well, I think one of the things that I mentioned it earlier that I'm really interested in, I like to explore is edge compute, right? Is moving, not sending that data back to the cloud, not sending people's private information back, doing the computations locally, and then providing just the output, right? And that can protect a lot of privacy. So you can even do it on video images, audio, things like that, where you can do the analysis locally and not have to send recorded audio, video files up to the cloud where they're subject to attacks and being compromised and things like that. So to me, I think, as we see, edge compute power increase and costs decrease, that's a really interesting opportunity to kind of bring privacy back into some of these devices.
I agree.
Or maybe for some of the applications, just get rid of the edge and do the processing on the device itself, if possible. Or use things like scrambled timestamp sequences that we have in ultrawideband for secure payment solutions, in which we just scramble a timestamp sequence, and we help ensuring that critical information, like for example validation of distances to the payment terminal, is held safe and secure and cannot be intercepted or manipulated, for example.
Okay. And Marcus, did you have something to add?
Oh, just one quick. It's privacy is a two-edged sword. Okay. One of the cool activities you can do, for example, cool things you can do is, for example, a fall detector, right? An elderly, my mom one time fell and she hurt herself. You can detect a deceleration with a radar in the bathroom and tell that someone had a fall and automatically call the paramedics. Okay. Well, at the same time, I might not want someone else to know what I'm doing in the bathroom. All right. So it's a two-edged sword, and I think it requires some careful management and some policies regarding that will be developed as time goes on.
And I think it's important to communicate that the algorithms have to be trained to look for like the fall. So it's not like the interference that your body is generating within space. It's not like they know this without being trained on it. So you don't have to, train people to look for people having sex in illicit spaces. That's something that actively needs to be done. So I feel like that's an important thing to recognize here. Okay. Oh, let's see. Oh, okay. That was more of a comment. Someone asked about Thread, and I know Thread is not a sensing technology, but I understand that people who are in the, especially in the smart home space, are like, so many wireless technologies. Thread is a communication technology, but how does Thread differ from UWB? Yeah, y'all are like, wait, that doesn't even make sense, but let's give it a whirl, because it is a legit question where people are like, oh.
So I think,
Bill.
yeah, I think the key difference to recognize is that a thread is a protocol, not a like sensing or a communications technology, right? It's a software defined piece of the system of how those two things communicate, right? So like thread is often done over the 2.4 gigahertz band, same as Wi-Fi, right? You can have 2.4 gigahertz Wi-Fi, you can have thread communicate over 2.4. So it's more, I'm trying to think of how to describe it, like an agreement between the two devices of how they are going to share data over that band. And so it's, it really is a completely different thing than ultra wideband, which is that's more on the radar, the RF technology side of the spectrum.
Got it. And oh, here's a question. Do any of these technologies use triangulation from multiple radios? I know we've talked about antennas, but I don't know if there's a question. Or...
Yeah, maybe I can say something about that.
Okay, I was like,
yeah.
Anyone?
Yeah, so I mean, with Wi-Fi, that's kind of one of the big advantages is you have devices all over your house. So it is very possible for you to perform measurements from different devices and, position more precisely through triangulation or through whatever means, targets or objects within the environment. So, because you do have devices spread everywhere, that's one big advantage that Wi-Fi has. And, triangulation is something that's certainly possible. And it's done, actually. It's something that has been demonstrated and is in the products.
Yeah, I've seen that definitely in some of the products. On any of, like, I don't know about radar or UWB. I'm trying to think about how UWB works and how that would. No, this is a big question for people who are building products. Right now, you throw these radios in. I feel like there's got to be a lot of work calibrating them. Is that something, if I'm a manufacturer, I have to do myself to kind of calibrate how the sensing is going to work? And are there resources to help with that?
Well, as a test and measurement supplier, right? That's what we do for a living. We measure.
Because it's like, call me.
Okay. So yeah, the test equipment companies all have equipment to measure, calibrate, and make sure devices are behaving properly. They're not interfering with other devices, and they're in compliance with things like FCC rules.
I guess I'm thinking more of like validating the algorithms for use in the real world, and like what that process, if I'm putting these sensors in my products, how do I make sure they work with my algorithms and they're delivering the right information, and what kind of time should be spent? Like, how long would that take me as part of like that process? And this may be a Ramona or Bill question.
Okay.
Okay, how much time it's gonna take? I don't think I can quantify. So I guess because it depends on so many things,
Or what does the
type of
process look
product,
like?
the use case, the environments where do you want to use this, the scale, the areas, the large scale operational areas, energy efficiency. So you have to look at all these kind of things.
Okay, so it's not easy. So if I'm going to start putting weird radios for sensing in my devices, I need to have probably an engineering team, it sounds like, who's really good at radios.
The engineering team or testing team, you have to write a proper methodology in the house developed for testing the radio and the application that is running on top of the radios, because it's not only about collecting the data, but also doing something with the data, analyzing the data properly, collecting the ground truth as well, to understand if you properly collected what you wanted to collect, and everything around this.
This feels impossible for someone who wants to build something with this technology, then that isn't like an Apple or a Google. Oh, Chris.
Yeah, maybe just to say something, actually, the second paper that we published just last year through the WBA, actually talks just about this. So we took one use case, this was home monitoring, and we created what we call a test methodology. So it outlines what exactly should be an approach to test a system like this. So we talk about, deploying them through the house, picking the position, coming up with a way to walk through the house in a very defined manner. We talked about, how do you synchronize the ground truth to the sensor output? How do we analyze the results? And how do we compare this with what's expected? So take a look at that paper if you want some more details, but it's a hard problem. It's a lot of work.
Maybe to chime in something just at the end there, which is if you're going to do that, get a good data scientist, right? Those people are trained to understand how to process these large data sets and extract something useful from them. And they're invaluable members of the team when you're trying to do something like this.
Okay. Oh, here's a good question. With radar and LiDAR, is it possible to have no-go areas or block out certain parts of the home, like the bathroom?
My guess is that with the Wi-Fi method, you could, since you have knowledge of where the transmitters are and where you are, you should be able to have some rough location ability that you could say, hey, don't do anything here because that's a no-go area.
So that's with Wi-Fi, but with LiDAR and some of the others, it's just, you would have to do that after the fact, just with math, just say don't.
Correct, yeah.
I'll say LiDAR is so highly directional that you could position your sensors in such a way to ensure that you're excluding certain areas, but outside of that, it would be difficult.
Yeah.
Okay. It is an all-seeing eye. Okay. Let's see. Oh, there was one other question. I'm coming back to it. And we'll probably end on this question. If you have a really awesome question, let me know. Oh, are there open source tools to play around with Wi-Fi sensing?
Not so much yet. There are some implementations from different chipset vendors, which kind of have made their way through the academic community into the hands of, I guess, more or less open source. But because they're very heavily dependent on proprietary components, right now it's you don't get access to everything. So there are limitations, but because it's an active area that the academic community is really interested in, there are tools and there are components around. So yeah, I guess hopefully when 802.11bf comes out, this will maybe accelerate that a bit and open up the ability to get some of this information more easily.
That feels like the standards solve everything kind of answer. When in fact, we all know that that is not the case. Okay, I want to end with y'all talking about like either a current project that uses some of these technologies that excites you, that you feel is truly innovative, or something that you think you could use these to build that would be like a dream product that would be kind of fun. So get your thinking caps on. I'm going to start with Bill first because he builds stuff for a living. So I feel like he must have something.
I think one of the most exciting uses of LiDAR that I've seen in the last few years has been foliage penetration and being able to basically look through a forest and see what's happening below it, right? And like that to me is, it almost feels like magic, right? To see, you can fly over this dense forest and then extract a map of what's going on underneath the trees. And so I think that's such a neat application that allows you to do so many interesting things. Like we talked about archaeology earlier, like finding these ruins that are, in a dense forest that might be hard to get through and to look at. And then the other area I think is, we're moving more and more to autonomous vehicles, not just cars, but, drones. There's a huge, the urban air mobility movement keeps gaining more and more traction. And I think LiDARs will be a constant presence in that field of finding better and more accurate ways for these vehicles to navigate without a human at the wheel, right, or at the joystick, so to speak. And so I think that will be a really cool area to see these products continue to develop.
Marcus. Oh,
Okay.
Ramona. Oh, sorry. We'll go to Ramona.
Okay.
Sorry.
Okay, Ramona, go ahead.
Okay, so Ultra-wideband, I think, because of its precision indoor, ultra-wideband location is fueling a new generation of AR and VR applications, which is going to allow simultaneous position data combined with high security communication. So I see it there. And of course, somewhere where it's already used in real-time localization systems, where it's perfect.
Mm-hmm.
In terms of
accuracy. Honestly, I want my own personal UWB radar that I can wear around my house or is built into like my wearable. And then I guess that would take a lot of power. Okay, we'll think about that some more. But I want basically for my home to be like, you're sitting on the couch. Tell me more, Ramona.
It depends with how many devices you have to range.
Okay, that's true. Okay. But yeah, I want it to be like, oh, she's sitting on the couch, you know, she's probably reading, let's keep the lights dimming up for her as it gets dark. I mean, I want magic. And I feel like UWB is going to be the contextual key to give me that magic. Okay, Marcus, products.
So the thing that excites me the most is we've got to push things a little bit further in frequency, okay? And this is as you get into the terahertz range, you've got molecular resonances. It's possible to uniquely identify organic molecules by the molecular resonances. So imagine having a UWB device on your cell phone that may be a radar, but you can aim it at your orange juice and detect if there's any non-organic chemicals in there, okay? Or there's also some things you can do for medical diagnosis using that technology. You can detect, one company in Israel is talking about using to detect coronavirus. So the ability to use sensing, go a little further in sensing and detect molecules is the one that I think is going to change the world.
So 5 years, stay tuned for my terahertz RF
there you
sensing
go.
panel. It's super cool, but we don't have the chips for that. We don't have I mean, that's military grade right now. So, but I'm excited.
Mm-hmm.
Okay, Chris.
Yeah, I don't think I can top that, but what
you can pick something that's real today.
Yeah, we can talk about something that's real today. I think for me, what interests me and excites me the most is some of the elder care and wellness products, because we have a more tech-savvy aging population, and they want to maintain the same sort of lifestyle that they have. And the way that they can do that is through some of this technology. So I really see that this is going to have a major impact on how people age in their house, and how they can use this technology to maintain their lifestyle. So this is something that it's near to future. So it's something that is within the realm of possibility in the very near term. So that's why I'm quite excited about the elder care and wellness products.
Yeah.
But I can say one more thing that's pretty cool. This is maybe a far out there thing, is in the 802.11bf discussions, one person actually came up with an idea and they showed some data to prove that it's feasible. They were able to show that sensing can detect sneezes. So in the COVID world where, this is a concern, we can use these, these signals to detect cases like this. So a lot of cool stuff you can do. It's just up to our imaginations.
I agree. Okay. Well, everyone, thank you so much for joining us today. Thank you, audience, for your questions. And if you didn't have questions, I hope you learned some things. And I would love to see everybody get started building very cool RF sensing products that, sure, even the terahertz sensing products. I would like those as well. So thanks to the panel, round of applause, and have a wonderful rest of your day.